Hello. Yeah! Gonna wait until we have 20 people. Then I will get started. Dum-de-dum. Got a very upset cat. Keeps meowing. Ivan? Dum-de-dum-de-dum. These people are tardy. Come on. Get above 20. Come on. You can do it. Awesome. Okay, there. We're at 20. I will begin. Hello, everybody. I wanted to let you know that I'm working on submitting the first grades into Q. So you can expect those by the end of the week at the latest, possibly today, depending on how efficient I am at doing the other things I have to do. All right, so, and please let me know if there are any issues with, occasionally I mess up. Today is quiz 6. Kinematics quiz 6. All right, so I'm going to get started here. So in the last class, we learned 3 equations that are called the kinematics equations. The first one said that delta x equals v naught t plus 1/2 a t squared. The second one says that v final equals v initial plus a t. And the third one says that v final squared equals v initial squared plus 2a delta x. So these are called the kinematics equations. And there is one important thing about these equations that you need to know. You need to know when you can use these equations, okay? And use only when the acceleration is equal to a constant. If the acceleration is not a constant, then these equations are not applicable, okay? So how did we use these equations the other day in our last lesson? Well, what you want to do is you want to parse the problem, and you're going to find 4 variables in that problem, 4 different variables. One of the variables is going to be an unknown, and you choose the equation that has those 4 variables in it. Okay? So that's how we apply the kinematics equations. So what are we going to be talking about today? Today is basically an extension of that last lesson, but we're going to focus on using the kinematics equations when gravity causes the acceleration. Okay. It turns out that gravity causes an acceleration that is approximately constant. It's not exactly constant, but it is approximately constant, and it's good enough. We're going to take it as being constant in this class. Things that could make gravity not constant would be if you threw something way high in the air, like hundreds of miles in the air. Okay? If you threw something hundreds of miles up into the sky, then the projectile is getting so far away from the Earth that gravity actually gets weaker. Okay? So we're not going to worry about situations like that where something is being thrown way up into the air. Okay? Another thing that can affect gravity is the local geology. If, for example, if you're living right above a particularly dense rock underneath the surface, then that could make gravity for you locally slightly larger than it is away from your house because of the presence of particular minerals underneath the surface that are denser than the average. And another thing is that gravity is is affected by your latitude, because the Earth is actually not a perfect sphere. It's kind of like if you took pizza dough and you spun it, the pizza dough flattens out. So the Earth is actually a sphere that is slightly flattened. So if you go to the equator is bulged out because of the spinning of the Earth, and so you're actually farther away from the Earth if you're farther away from the center of the Earth if you're on the equator versus where we are. And you're actually closest to the equator, or closest to the center if you're standing on the North Pole. Okay? All right. So what is the size of the gravitational acceleration? The gravitational acceleration is negative 9.81 meters per second squared. Okay? This is the global average. As I said, it depends on local geology a little bit. It depends on latitude a little bit. But that's the accepted average. Why is there a minus sign? There's a minus sign because gravity pulls down. Okay? And so we are going to be using the convention that upward is positive. So saying that A equals plus 9.81 meters per second squared is like saying that there's anti-gravity or being accelerated away from the surface, okay, which doesn't make any sense. So, yeah, we will approximate this, and all of the homework, none of the homework uses acceleration as negative 9.81, okay? I have it programmed in there to approximate gravity as 10. So it's very standard to approximate gravity as 10 unless you're doing really precise calculations, okay? We're not doing ultra precise calculations, so we don't have to worry about that. So all of the homework this year, even though the true value is more like 9.81, I have it programmed in as 10, okay? So negative 10, downward with an acceleration of 10 meters per second squared. we would say that the magnitude of the gravitational acceleration is denoted by G, and the magnitude, whenever I say magnitude, that basically means the absolute value. So I'm not going to say that the magnitude of the gravitational acceleration is negative 10 meters per second squared. I'm going to say that the magnitude of the gravitational acceleration is 10 meters per second squared. Okay, so you just kind of, sometimes in physics the sign is really important, and sometimes it's not. So if we're just comparing the sizes of things, we compare the magnitudes. Okay. This is, of course, the acceleration due to gravity on Earth. If you go to other astronomical bodies within our solar system, the gravitational acceleration is different. Okay? So, for example, gravity on the Moon is only 1.6 meters per second squared. It's about 1/6 what it is on Earth. Gravity on Mars is about 3.7 meters per second squared, so it's about 1/3 of what it is on Earth. Okay? Incidentally, that means you could jump 3 times as high on Mars and 6 times as high on the Moon. That's, of course, provided you didn't have a spacesuit on that inhibited your motion. The gravity on Jupiter is more like 20 meters per second squared. So the gravitational acceleration varies from planet to planet. Unless otherwise stated, so unless I explicitly say this event is happening on the Moon or this event is happening on Mars or something like that, unless I say that explicitly, you're going to assume that what is happening on Earth, and if it's flying through the air, it's accelerating due to gravity. Okay, so you're going to use negative 10 meters per second squared as the acceleration. So the remainder of this class is just going to be more practice with the kinematics equations, but in the context of something flying through the air. Okay, and whenever something is flying through the air, above the surface of Earth, we're going to use an acceleration of negative 10 meters per second squared. So let's see. An egg is released from 75 meters in the air. Okay? How much time does it take? To hit the ground? Okay? So remember, when we are using the, hang on a second. Okay, so we have a really good question that I missed about the acceleration due to gravity on Jupiter. Why isn't it much higher than 20? There are two factors at play here. One is the total amount of mass that the planet has. So Jupiter is, 1,000 times more massive than the Earth, literally 1,000 times more massive. However, the other thing you have to consider is how far away from the center of the planet is the surface. So in addition to being incredibly massive, it's also incredibly large. And it turns out that because it is so large, that reduces the size of gravity. Okay? Why is gravity so strong next to a black hole? It's because the surface of the black hole is much closer to the center. All right? The surface. It doesn't really have a surface, but yeah. Okay. So let's go ahead and parse this problem for information. The egg is released from 75 meters in the air. That means the egg has to fall 75 meters. So we're going to have delta y is negative 75 meters because it falls that amount. Okay? When you say something is released, released is code for initial velocity equals 0. Okay? If I said I threw the egg with a certain speed, that means the initial velocity is not 0. But if you just release something, you're not throwing it up or down. Okay? You're just letting it go with an initial velocity of 0. How much time does it take to hit the ground? So T is the question mark. And then lastly, we're assuming that this is happening on Earth. Okay? So we have an acceleration of negative 10 meters per second squared. So go ahead and put it in the live chat. What do you think is the correct kinematics equation to use in this scenario? 1, 2, or 3. And while you were thinking about that, I just wanted to give an application of this type of problem. Okay. How can you use equation number 2? Equation number 2 has final velocity. Final velocity isn't in our list of unknowns, so we can't use equation number 2. So it's got to be equation 1, right? In order to use equations 2 or 3, final velocity has to be part of the problem. So for example, if I had said, how fast is it going just before it hits the ground, then I would be asking for the final velocity, in which case you would use, 2 or 3. But because I don't care about the final velocity, I'm going to use equation 1. And I'm going to write that like delta y equals v initial times time plus 1/2 at squared. Okay? You can write it as delta x or delta y. Generally speaking, delta x refers to horizontal motion, so I'm writing it as delta y just to emphasize the fact that this is vertical motion. Okay? So now I plug in numbers. I have minus 75 is the vertical displacement, so downward 75 meters. Initial velocity is 0, so that is going to kill this first term. So this term just goes away because the initial velocity is 0. 1/2 a is going to be half of negative 10, which is negative 5. So I have negative 75 equals negative 5t squared. All right. Divide both sides by negative 5, and I would get 15 equals t squared. And then I take the square root. T equals square root of 15, which is 3.9 seconds. So it would take 3.9 seconds to hit the ground. This is only an approximation. Okay? The reason I say that is because if you are launching projectiles near the surface of the Earth has an atmosphere. So this is the acceleration caused only by gravity. But there are other things that can cause an egg to accelerate, like air resistance. Air resistance is going to tend to reduce the acceleration because as the egg falls, the wind it's moving through a fluid. The air is really a fluid that is all around us, and there's resistance to move through a fluid, so it would actually take slightly more than 3.9 seconds. The higher the speeds involved, the bigger the deviations are going to be. If the egg was released from an extremely high altitude where it has the opportunity to build up a lot of speed, then air resistance is going to be more dominant as a factor. So this is only an approximation. If you take my AP Physics C class, we talk about how could you do this problem accounting for air resistance. All right. If, however, I said this egg is released from 75 meters above the surface of the moon, this answer, if again, I would have to use a different acceleration, but the answer obtained by this method would be significantly more accurate, okay? The reason is that the moon does not have an atmosphere. So you don't have any air resistance while the egg falls. So gravity is the only factor influencing the motion, and it would be extremely accurate. All right. I did want to talk really briefly about how you could use this. There's a fun little exercise you can do. I think it's the Wednesday extra for this week. If you have a friend hold like a ruler or something. I don't have a ruler next to me. Oh, I have this piece of steel. I don't want to drop that piece of steel. Okay, so let's say you have a friend hold a thing, okay, and you hold your fingers out. So I'm not holding on to I'm sort of waiting, and then your friend releases the notebook at random. So this is your friend's arm. This is your friend's arm. This is your arm. Your friend releases the notebook at random, and you catch it as fast as you can. Okay? And then you measure how far did it drop. Okay? So that is going to be your delta y. Because this was just released, its initial velocity was 0, the acceleration is -10. You could solve for the time. That was the time it took for you to catch the ruler, okay? Which is your reaction time. So you could use the distance that it falls to determine your reaction time, which is kind of fun to do, all right? Yeah. Okay, let's move on to the next example. Old Faithful. You guys know what Old Faithful is? It's a geyser. Erupts, launching water into the air. We'll say launching water 45 meters into the air. Okay. The question is, how fast does the water emerge from the geyser? Okay. How fast does the water emerge from the geyser? So let's kind of draw a picture of this just so everyone understands. Here's the ground. And then the geyser erupts. So the water comes up like this. Kind of looks like that. And I'm saying that the height of this column of water is 45 meters. Okay? And what we want to know is how fast does the water come out? Okay? Now, of course, immediately after the water emerges, it's going to start to slow down because gravity slows it. Then once it reaches its apex, gravity then speeds it back up. All right? So we want to know what is the initial velocity of that stream of water. So we have V initial equals a question mark. We have delta y equals 45 meters. We have the acceleration is equal to -10 meters per second squared because Old Faithful is on Earth. And then lastly, We need one more piece of information because we always need 4 pieces of information for a kinematics problem. And it has to do with the highest point. Okay, so we're considering this when the water leaves the geyser, that's the starting point. And we're considering the highest point to be the end of the problem. Okay, and at the highest point in the motion, the final velocity is 0. Okay, that's an important, I'm going to put 2 stars next to that so you remember that the velocity is 0 at the highest point. Why is that? Well, what if one of the things you do in math class is you consider, well, what if the opposite were true? What if the velocity was not 0 at the highest point? Okay, if the velocity was positive at the highest point, then that would mean that what would happen if you waited a little bit longer? It would continue to go upward. If the velocity is positive at the highest point, that wasn't really the highest point because it was still going upward. Okay. What if the velocity was negative at the highest point? Then that means that at the highest point it was already going downward, which meant that just a moment before it came from a higher location. So if the final velocity is negative, that wasn't really the highest point. So what's the only number that's not positive or negative? It's 0. So the final velocity has to be 0 at the highest point. I'll wait. Go ahead and tell me which equation are we going to use to solve this problem. Good. People are typing in 3. Excellent. Very good. So we're going to use v final squared equals v initial squared plus 2a, and normally it's delta x, but because it's vertical motion, I'm going to write delta y. Okay. So v final is 0, so that means v final squared is 0. V initial is what I'm trying to figure out, so I leave that as a variable, plus 2 times the acceleration is -10, and then delta y is 45. So I have 0 equals v initial squared. This all multiplied together is 900. So I add 900 to both sides. And then I take the square root, and I get that the square root is 30. So that means that the initial velocity is plus 30 meters per second. Now, those of you who are persnickety, that's a good word, persnickety. That means you're kind of like detail-oriented. If you are persnickety, you know that when you take the square root, it could be plus or minus 30. So how do I know that it was plus 30? Well, the geyser does not erupt downward, it erupts upward. So I used the context of the problem to choose the positive root of that. Okay? Okay, let's go to the next example. You throw a penny upward at 7 meters per second. All right. 5 seconds later, it lands in the bottom of a well. Okay. What was the speed at which the penny hits the surface? Okay. So we're not, if I wanted to give you a tougher problem, I could say, well, what would happen if you heard the splash 5 seconds later, in which case you'd have to take into account the time for the sound to travel up the well. That would be interesting, but I won't do that to you. Maybe I'll make that a Wednesday extra sometime. What was the speed at which the penny hits the surface? Okay, so we have, you throw the penny upward at 7 meters per second. So that means that V initial is plus 7 meters per second. The time is 5 seconds. The acceleration is negative 10 meters per second squared. And we want to know what was the speed at which the penny hits the surface. So we're asking for V final. So this is the second kinematics equation. V final equals V initial plus AT. So we're trying to get V final, so I leave that as a variable. V initial is 7. Acceleration is negative 10. Time is 5 seconds. So we get 7 minus 50, that's negative 43 meters per second. Now one little thing here. If I said what was the speed, speed is velocity without direction, okay? So technically speaking, my answer is 43 meters per second, not negative 43, because I didn't say what was the velocity at which it hits the surface. I said what was the speed, and speed is just a number without a direction, okay? So that's just a little like linguistic thing about solving the physics problem. We're going to do one more example. And then we'll transition over to the Zoom room. So I'm going to draw a little picture here because I like to draw. Okay. Cool. There's my picture. Your friend chokes on a chicken wing. Okay? You give the Heimlich maneuver. This launches the wing up at 25 meters per second. Okay? So the wing shoots up into the air, 25 meters per second is that initial speed. The wing goes up, comes back down, hits your friend on the forehead. Okay? So the question is, what is the time of flight? what is the time of flight? See what I did there? It's a chicken wing, time of flight. Okay, so let's go through this problem and figure out what the knowns are and what the unknowns are. So we want the time of flight, so that means t is the question mark. Okay. We know the wing is launched up at 25 meters per second, so that means that v initial is 25 meters per second. I don't know of anyone who has ever choked on a chicken wing in a place other than Earth, so that means that the acceleration is -10 meters per second squared. And then we need a fourth piece of information, and so this part is tricky. So if you think about it, if you throw something into the air, okay, and you let it land, the final velocity is 0, right? Because it hits the ground and it just stays there. But here's the thing. As this is falling, how does it come to a stop? It comes to a stop because it made contact with the ground, okay? And because it made contact with the ground, the acceleration is going to change, which is going to invalidate the kinematics equation. Because you have one acceleration while it's falling, and then another acceleration while it's decelerating to a stop as it makes contact with the ground. That's two different accelerations. So we cannot use v final equals 0. No. Do not say that. Okay? What would it mean for the final velocity to be 0? That would mean that it was just sort of like hovering above the ground. Okay? So actually, the way that you want to solve this problem is you want to say, well, the chicken wing started at this elevation, and it goes up and it comes back down, and it ends at that elevation. So the initial elevation is the same as the final elevation. So delta y equals 0. Okay? So make sure you understand that, why that's true. I'll put 2 stars next to it. Delta y is equal to 0. Okay? That's only in the case that it comes back to the same elevation. So once we use that delta y equals 0, we can then see that it's the first kinematics equation. Delta y equals v naught times time plus 1/2 at squared. Delta y is 0. V initial is 25. I leave time as a variable. Acceleration is -10, so half of -10 is -5. I add 5t squared to both sides. 5t squared equals 25t. Divide both sides by 5. T squared equals 5t. And then I divide both sides by t. I have to be a little bit careful here because whenever you divide by a variable, you have to make sure that that variable is not 0. Okay? Now, does it take a finite amount of time for a chicken wing to go up and come back down? Yes, it does. We know that it's not an infinitely fast chicken wing that goes whoosh, like that. It takes time for the chicken wing to go up and come back down. So time is not equal to 0 seconds. Time is a positive number. Okay? So that means we can, in fact, divide by the variable t. So the t's cancel out here, and then t squared cancels with t, and we get that it's going to take 5 seconds to come back down. That's the time of flight. All right? So that's my lesson for today, and I will see you in the Zoom room. Ta-ta for now.